Okay, so just to give you some discussion on what we're talking about here when our goal is to estimate a population proportion, pretty much impossible to get a true proportion for the entire demographic of the United States adults, 18 to 34. Whatever your subject matter is, sometimes the population is just impossible to address the entire population. So you have to rely on some sample, and if you do a good job obtaining your sample so that it's got a good representation of cross-section of each of, you know, the different groups that are in your population, then your point estimate or the data you retrieve from your sample should be a pretty good representation of the overall population. So since we can't practically obtain the population proportion, what we'll do instead is make an estimate, and we'll say, you know, we got this sample data and it came in here, and we think that within a margin of error of below this result and above the result from our sample, we think the true proportion lies in there. And not only that, we're 95% certain, or we're 99% certain that the true proportion is within that range. So we get a point estimate, we subtract a little, we add a little, and we create this interval, and we say we think the proportion is inside that interval. And this is how we do it. So okay, so it all starts with this point estimate. Okay, and so a point estimate is just the statistic that comes from your sample. So we create, and we call that p hat, and x is the number of individuals with the characteristic of interest, and n is the sample size that we used. Okay. All right, so let's look at an example here. We're going to calculate the point estimate. In July of 2008, a Quinnipiac University poll asked 1,738, so that's N. So this is the sample size, 1730, or oh, it says 83, sorry, 1783. Registered voters nationwide, whether they favored or opposed the death penalty for persons convicted of murder. And out of these 1783, 1123 were in favor. So that was the number in favor. To get our p hat, we call that x. Okay, so p hat equals the number that have the characteristic over n. So that would be 1123 over the 1783. Okay, so all we're doing now is obtaining the point estimate. So I've just done that. And they do it here on the next slide, and in a decimal form it's 0.63. Okay, so that's kind of an estimate for the actual proportion of registered voters that would favor the death penalty for persons convicted of murder. Okay, so what we do with that now is we're going to create that confidence interval I was talking about. So the confidence interval is somewhere between a lower limit subtracted from our p hat and an upper limit added to our p hat, and that's what we call the margin of error. But remember I said we wanted to be like 95% certain or 99% certain. That's the level of confidence, and it all depends on alpha, and we call it a 1 minus alpha times 100%. So if we wanted, for example, if we want or use an alpha equal to 0.05, then what is our level of confidence? Anybody? If we locked in an alpha of 0.05, what would our level of confidence be?
95.
Correct. Yeah. So if I take 1 minus 0.05 and multiply it times 100%, well, that's 0.95 times 100%, so that's 95%. Okay, so if I give you a level of confidence, you can just take that, so let me ask you in the other direction. If our level of confidence is 99%, what is alpha? Here I gave you alpha and you said, okay, it must be a 95% confidence level since you used 0.05. Think in the other direction, what is alpha if we're using a confidence level of 99%?
0.01.
0.01. Okay, so really it's just the complement of the decimal form of the percent, level of percent. Typically we'll find a 95 or a 99, so you'll see there are some common ones. And in fact, if I go back to this here, and table 5, some of the common levels of confidence are shown here: 90, 90%, 95, 98, 99. Okay, so let's move on, and we got to figure out how do we calculate that little scope or that interval around that we pad our p hat with. It's our confidence interval. Okay, so a 95% level of confidence implies an alpha of 0.05, and that if we took 100 different confidence intervals, each based on different sample from the sample population, we would expect 95 of those intervals to contain the parameter, and 5 would not include the parameter. So we're just saying that if we took, once we create this, based on some level of confidence, we're like 95% certain that the true parameter falls within that interval. So we'll see a good way to word it here once we get an example. Okay, so we're just going to take our point estimate. Remember we called this p hat, plus and minus, and we'll use a capital E to represent the margin of error. So that creates a lower bound and an upper bound. Within this range, we believe with 95% confidence that the true proportion exists. Okay, some things about level of confidence. As we increase the level of confidence, the margin of error is going to get larger, because in order to be that confident, we have to widen our scope a little bit. But if we increase our sample size, then the margin of error decreases. So we can kind of play with those parameters to kind of determine how much range we want within our confidence interval. Okay, and another situation here is if the standard deviation of the population is larger, then our interval is going to be wider no matter what the level of confidence that we're using. So some of those things might be intuitive for you. Okay, so here's some of the formulas. So if we've got a sample size n, and we have the sampling distribution of p hat approximately normal with mu of p hat equal to p, and the standard deviation sigma of p hat is square root of p times 1 minus p divided by n, provided n times p times 1 minus p is greater than or equal to 10. So that was our normality check. So some of this is familiar from last section. And we've also got that independence requirement that our sample is no larger than 5% of the population size. So this is kind of a reiteration of the sampling distribution of p hat. Qualifications in the formulas to recalculate sigma of p hat. Okay, so the 1 minus alpha times 100% confidence interval. We already said that. All right, so let's get to this is the big stuff here. This is how you calculate your margin of error. So this particular part right here is E. So if we just think of E as this Z sub alpha over 2 times the square root of p hat times 1 minus p hat divided by n, then we can think of our lower bound is just going to be p hat minus E. So we can think of the confidence interval as p hat plus and minus E. Okay, so that's all this is saying. If we let this little portion be called E for the margin of error, we subtract it from p hat and we add it to p hat, then we've got the bounds of our confidence interval. And whatever alpha is going to determine the level of confidence. Okay, so those are the big formulas of the day right there. Okay, so here we call it E, and we can make it a little more concise. All right, so now we're going to put this to work. We want a 90% confidence interval for the proportion of registered voters who are in favor of the death penalty. So remember, our N was 1783. And our p hat, what was it, 0.63? Yeah. Okay, and that was just the 1123 out of 1783. Okay, so what's alpha? For this particular confidence interval we're creating, what's alpha?
0.1.
All right, 0.10. Okay, so 90% confidence tells us alpha is 0.10. So let's create E. Okay, so we have to go get Z alpha over 2. Now, alpha over 2 is going to be 0.05. So Z 0.05. Remember, this is the Z-score whose area under the curve is 0.05. So let's go to the table. And I could look through and sort through all of these here and find 0.05, or as close as I can get to 0.05. And this is the territory here. So 0.0409 and 0.0505. So we're looking somewhere around negative 1.645 maybe. If we come down here, for a 90% confidence interval, you've got a shortcut down here. So my alpha over 2, if alpha is, so it's a 90% confidence interval, then 1.645 is our alpha over 2. And again, you can see that when you come here. Okay, and the reason this is negative 1.645 is because this is the area to the left of the curve. And remember that Z sub alpha notation asks for the area where this is to the right. So we're just going to complement it. Okay, so we're going to use E is equal to 1.645 times the square root p hat, which is 0.63, times 1 minus 0.63, so 0.37, divided by n, the sample size, so 1783. Okay, and so they've calculated for us on this next slide that the lower bound is about 0.61. And if I add the margin of error calculation to p hat, so this is just p hat plus and minus e right here. Okay, so our lower bound for the confidence interval is 0.61 and our upper bound is 0.65. Okay, and this is the qualification test to me that n times p hat times 1 minus p hat is greater than or equal to 10. Well, it's certainly way greater than 10. So, okay, so our conclusion is that we're 90% confident that the proportion of registered voters who are in favor of the death penalty for those convicted of murder is between our lower bound and our upper bound, 0.61 and 0.65. Okay, so that's obtaining a confidence interval, and you got a shortcut for critical value Z alpha over 2 here. If the level of confidence that you're using is not shown here, then you'll just want to look up the score here. And since this is the area to the left, you'll have to take the opposite sign. So if I find my sub alpha, Z sub 0.05 is, like I said, about right in here. So negative 1.64 and then halfway between 5. So they just interpolated between 0.04 and 0.05. But just remember to make it positive because it's on the other side of this. I would have to move this over here to get the area to the right that matches that. Because remember, this is 0 here, and positives on the right, negatives on the left. And then chapter 9, this is like a quick shot of the particular formula that you're going to be using. So this is what we looked at. That. Okay, another thing we can do, and this is pretty useful, is that we may want to figure out how large of a sample do we need to obtain a specified margin of error. If you want to be within some margin of error, how large of a sample do you need? And this is our formula for that. So we're just going to take p hat times 1 minus p hat and then multiply that by Z alpha over 2 divided by margin of error that we want, quantity squared. Okay, and here's the situation. Since we need p hat before we even get started, we're going to have to rely on earlier data or some form of p hat that we've got from a sample from the population. And if you see where p hat is as large as possible, that's a maximum for this curve. So if we defaulted p hat to be 0.5, then we're going to overestimate our requirements for the size of our sample by as much as we could need, because any other p hat is going to fall below 0.5 in terms of this curve for the p hat times 1 minus p hat. Okay, so The other thing you want to do is just round your result up to the next integer, because you're talking about the size of a sample and you can't get a portion of an individual from your sample. Okay, so let's say that a prior estimate of P is not available. Then we'll use this formula here. Okay, so I'm going to give you guys a minute to try this out and find N. We got a sociologist wants to determine the percentage of residents of America that only speak English at home. So how large of a sample do we need to obtain if we want to be within 3 percentage points and a 90% confidence level? Okay, so she's going to use a point estimate from a census in 2000, and that result was 82.4%. Okay, so that gives you a p hat to work with in this particular case. Okay, did anybody come up with an N for this? So for the 3 percentage points, basically your E that you'll need to use is that. Okay, so plugging in the parts to your formula, what we need is N is equal to 0.824. So there's our P hat times 1 minus 0.824. Okay, so that would be 0.176 is 1 minus 0.824. So P hat times 1 minus P hat. And then we got to take that times the square root, or not the square root. We need Z of alpha over 2. Okay, so we said that's 1.645. And remember, you can look here on table 5 for 90% confidence. Divided by the 0.03. And then this quantity is squared. Okay, so since we get 436.04, we can't take 0.04 worth of an individual, so we're just going to go ahead and round this up to the nearest integer. Even though in terms of mathematical rounding, we wouldn't round, since what we're doing is deciding how large of a sample to use. We don't want to underestimate, so we're always going to round up. Okay, so that way, remember we said that we have to play with those parameters and decide what our priorities are. So obviously we can't get the actual parameter from the entire population, but how big of a group do I need in my sample if I want to be within a margin of error of 3% and also have 90% confidence in my estimate. Okay, so that's kind of a rundown of the estimating a population proportion. Do you guys have any questions about that, or any? Are you stuck on any of these concepts, any of these slides? Let me ask you this, just before we wrap. Let me ask you for a Z alpha, Z sub alpha, a couple of them. Okay, so I'm going to go over here. Okay, so my question here is, let's say that we're using let's say alpha is equal to 0.05. Okay, use the table, and even if you can use the shortcut, even if you think you can use a shortcut, I'd like you to use the table and find Z sub alpha over 2. Okay, so Z sub alpha over 2 would be Z 0.025, right? If I take 0.05 and divide by 2. So we have to go find .025 in table 5. Okay, so that's kind of hard on your eyes, but here's 0.0202, here's 0.0256, bingo. We've actually got an exact, we don't have to interpolate. So I come over here and it says negative 1.96. But remember, this is interpreting this as the area to the left. And because the normal distribution is symmetrical, I can just jump over the 0, and the area to the right would be identical to the area to the left. But instead of being negative 1.96, it would be positive 1.96. So we can say that, okay, Z sub 0.025 is positive 1.96. Now, if you recognize that an alpha of 0.05 implies a level of confidence of 95%, then you can look down here to your shortcut table and you can say, oh, for a 95% confidence, I need to use 1.96. But notice your shortcut table has only got 4 different levels of confidence. Now, those are the predominant ones that you'll be working with, which is good. But if you were asked for something like 97% confidence, and then you'd have to go get your Z sub alpha and find your alpha, and then negate, remember to negate the Z because you got to jump to the other side, since Z sub alpha notation refers to the area to the right of that alpha, whatever the subscript to Z is. Okay, so those are the parts that you'll need in the formulas. Now, so for your online assignment, it probably gives you the ability to just like click on something and it'll bring up table 5 for you, or some things that you might need might be readily part of that question. I would suggest that even though they have those, go get it from the PDF file that I posted on Blackboard. And the reason I say that is because when you take your final, I'm planning on your final being a Blackboard exam. So that'll be kind of like, you know, there'll be multiple choice options maybe, but there won't be any of those little hot links to table 5 or whatever. You'll have to kind of fend for yourself and go grab that PDF and find it. So if you get accustomed to reading through that now, it'll be a lot less of an issue for you when the final comes along. So it's just a suggestion. You guys can do that however you want. Any other questions or comments here before we go ahead and let you loose on your assignment? And in our next class, we'll be doing 9.2, and it's going to follow this same kind of concept, but instead of estimating a population proportion, we're going to estimate a population mean. So we're kind of, excuse me, going in the reverse order that we went in 8.1 and 8.2. Okay. So if you have questions, just hang on and I'll stick around. And if you don't have questions, you can drop off, and your assignment on my lab should come, if it's not already live, it should come live within the next 20 minutes.